Okay. Hey everyone, thanks for joining. My name is Tom, and we're going to talk today about secret voting or confidential voting, but not just confidential voting, but decentralized confidential voting on a public blockchain, which is pretty cool. So we'll start with a few slides, and then we'll dive into some code. So first of all, a bit of introduction about myself. As I said, my name is Tom. I'm a blockchain engineer at Enigma MPC, which is a major contributor of the secret network, which is, if you're not familiar, is a layer one blockchain with encrypted smart contracts, and we will understand what that means in a second. So before we dive into specifically secret voting, we'll take a quick introduction to the secret network for those of you who aren't familiar, and just to give everyone a little bit of context. So secret network is a blockchain, as I said, is a layer one blockchain, and will let anyone perform computations on encrypted data. And that means that basically all the state of the blockchain is encrypted. And by that, we strive to bring privacy to smart contracts and to public blockchains. But why do we care about privacy at all? What's the motivation behind it? So today on traditional blockchains like Ethereum or Binance Smart Chain or even Terra, everything is public. This is the foundation of blockchain, right? This is the whole point. So in ERC20s, for example, in tokens, you can see the balances of everyone. You can see transfers. You can see, like, if I transferred X amount of tokens to a different address, and you can basically see everything. You can see my trades on Uniswap, for example. You can't store anything really sensitive, like sensitive data, on top of blockchain, right? Because everything is public. So you can't store, like, I don't know, personal data that you want to keep private. You can't store health or finance data, insurance data. You can store passwords or private keys of any sort. And even like games or turn-based games like poker or blackjack, you can really natively implement on top of like in a decentralized way, because everyone will see your hand, right? Everyone will see your cards. So that's not fair. And yeah, we also have the issue of front running, in which people or bots can just see into the transaction mempool and perform transactions or operations to their own benefit based on upcoming transactions. And we also can't really have decentralized randomness, right? Because if everyone can see the entropy or the state of the random number generator, so basically anyone can know what the next number is going to be, right? So it is pretty obvious that we need some privacy in public blockchain, and in secret network we make it possible to do in a decentralized way, which is very exciting. So yeah, as I said, we have something we call secret contracts, which are basically smart contract, but they perform computations on encrypted data. I haven't mentioned it, but we built like the network built on top of Cosmos SDK, the same as Terra. We run like the contracts run on top of CosmWasm, written in Rust. and all this, like the code should be pretty familiar to you. And like on a very high level, the way it works is that we have the contracts, right, on the like running in the blockchain. The state of the blockchain itself is encrypted, and all the inputs and all the outputs of the blockchain in and out is encrypted. So I send encrypted input into the blockchain. Let's say I want to interact with a certain contract. The nodes perform computation on top of this encrypted data, and then output the output that I get from my operation is also encrypted and only visible by me. So that basically how it works. And that was like background or a quick introduction about the secret network. So back to our use case, which is secret voting. So some technical stuff first. It will be very quick, just to like give you some context. We implemented secret voting to for our governance token, which is called CFI. CFI is a governance token of the secret swap ecosystem, if you're not familiar with. And basically, users lock their CFI in a staking contract and get voting power in the votes. So I can quickly show you how it looks. 1 second. It's pretty basic stuff. This is the governance page, and we have like this is mainnet. You like oops. People can go in here, create proposals, vote on proposals. We have, unfortunately, a lot of failed ones, but we have a proposal that passed as well. And yeah, pretty basic stuff. So what do we actually want to achieve in voting? Why do we need privacy in voting? So first of all, I'm not sure if I mentioned it, but the voting power I have is equivalent to the amount of CFI I hold, right? So we want to give more influence to strong players in the CFI ecosystem. So if I have, let's say, for example, if I have 1,000 CFI, I will get 1,000 voting power. So I will have more voting power than a person with 100 CFI. So first of all, and the most basic goal is that I don't want people to know how much CFI I hold or how much CFI I have locked in the staking contract. So that's pretty obvious. And maybe even more obvious than that is that I don't want people to know what I voted for, right? So let's say we have a vote. I don't know, do we want to eat dinner outside today? So I don't want people to know what I voted for. If I voted yes, if I voted no, if I voted like, if there's any third option. So that's two pretty obvious goals that we want to achieve here. And the beauty of secret network is that you basically get all this stuff for free. You get it by default. Because as we mentioned earlier, the balance of my CFI is encrypted, right? It's private. It's visible only to me because the state of the blockchain is encrypted. When I vote, let's say I vote yes for eating outside today, my input is encrypted. So my vote is counted for the tally of the option yes, but no one but me can see what I voted for. And that's why we're going to dive into some code right now. And you'll see that the code is pretty simple, right? Like there's nothing fancy we're doing to achieve privacy or anything else. It's pretty much the same as writing a regular contract, but you also gain the privacy benefits of it. So that's pretty cool. So yeah, let's dive into the code. By the way, if you have any questions, just drop them in the chat. I'll try to notice and answer them. And worst case, we'll have time for questions at the end of this talk. So let's just start with the init function. So basically, how it works is that you're having an echo. Is it bad? Is it a really bad echo? It's maybe the room. I'm sorry about that. I'm not sure I can do anything about it right now. All right. So let's start from the init function. The init function is pretty basic. Oh yeah, I was starting to say, just to give you some context, the way it works is that this contract is a voting contract, and we instantiate a new contract for every proposal or every vote. And specifically on our use case in the secret network, in the secret swap governance, we have a factory contract that calls and instantiates new votes. So in the init function, we just store a bunch of stuff, right? So we store the owner of this vote, which is usually, in our case, the factory contract, the sender of the init message. We store a bunch of metadata like the title of the vote, the description, the author alias. We have the choices of the vote, which means like the choices I can vote for. And what else? We initialize the tally object. Cool, the audio is fine now. So yeah, we store the tally object. The tally object is just a vector of U128, which will be synchronized with the choices vector, right? So the choices vector is a vector of strings. So let's say, for example, the choices vector will be yes or no. Sorry. And then the tally vector, which is, as I said, a vector of U128, will store how much voting power went into every choice. So, for example, we can, like the yes option will get 1,000 votes or 1,000 voting power, and the no option will get 500. Okay, so this is how it's going to look like. The choices vector and the tally vector. What else? We calculate the ending timestamp. So let me just let me show you the init message real quick. So we get, as I said, we get metadata, a bunch of config stuff, the choices, and you can pretty much ignore anything else. So where was I? Yeah, so we get the proposer of this vote sends the duration of this vote. So we calculate, it's just an epoch time in seconds. So we just add up the block time and the duration, and we get the ending timestamp. Pretty basic. We store all that, and that's pretty much it for the init function. Again, I want to emphasize that everything we store is encrypted, is private. By the way, the type store object you see here, you may be not familiar with it. It's a struct that a team member of ours created, which is basically storage access that serializes and deserializes using bin code 2. So nothing special here. You should be familiar with most of it. So for the handle messages. So again, we shouldn't have too many, right? We should just be able to vote and basically read the proposal's outcome. So let's dive into the vote function. What we have here, we first of all want the vote to be ongoing. We don't want people obviously to vote, after the vote has already ended. We query this is not really interesting. We're just querying the voting power from the staking pool. Like, as I said earlier, people lock their CFI in a staking pool to get voting power. So we query for the voting power here. We try to read if there are any previous votes this user has. We just want to read the existing one and update it. Let's see if we have anything special. No, the read vote function just reads, just tries to read any existing vote. And the update vote is a little bit more complicated, but really, but not really. It's like just fancy ways to update the tally without creating any problems with addressing any edge cases, like what happens if a user already voted, or a choice that was sent does not exist, etc., etc. So basically, this section is if previous vote already exists, we basically take the previous vote, we decrease the tally of this specific choice by the previous voting power, and then we add the new voting power to the new vote, the updated vote tally. If it doesn't exist, we just create a new vote and update the tally again. So again, nothing special. And yeah, the rest of it you can ignore for now, and we'll come back to it later. So that's basically the main function of this contract, right? We initialize stuff, and we have a voting function. We also have some queries. We can query the choices. One thing though about secret contracts is, because we are used, if you worked with Ethereum a lot, you know that basically every global variable you have stored in the state, you can just you automatically get a query for it. Not in our case, because to expose anything public, like, I want people to know what choices a vote has, right? A proposal has. So this is, although this is encrypted in private, me as a contract developer, I want to expose this data, and for it to still be public. So we do need to implement some queries, like choices, the tally, vote of a specific, like, I want to query my vote to see what I voted for and what my voting power was, number of voters, the info about the vote, etc. So yeah, that's basically it. We have all the functionality we need, basically. And as we said, we get a bunch of privacy benefits by default. But there are a few, like, when you design a secret contract. And when you have specific data that you want to keep private, you need to think about a few other stuff, which we will go over now. So let's think of something like this. We wanted we said in the beginning that what we want to achieve is, first of all, keep my voting power private, and second of all, keep my the choice that I voted for private, right? So let's think of something like this. Let's say we have a vote. Should we eat out tonight? And we have options yes or no. Oops. All right. Cool. And let's say I see this proposal and I decide to vote yes. Oops. One second, sorry. Okay, something weird on me. What's going on? One sec. Yeah, okay. So, yeah, sorry about that. So let's say I voted, oops. It's going to be hard. So let's say I voted yes, right? My name is Tom. And I voted yes for this vote. What happens if I'm the only one? I'm the only one who voted. What happens then? So the outcome, the result of this proposal will be yes. And let's say I have 1,000 voting power, and people will see that the result. Wow, this is going to be difficult. Sorry about my horrible writing. So the result will be yes will get 1,000 votes, and no will get 0. But the thing is that we can't hide who voted. Like we can't hide the transaction sender. So people that will look will be able to tell that I voted, and that only me was the one who voted. So it's pretty obvious here that I was the only voter, and that I voted yes, and that I have a voting power of 1,000. Right. So this is an issue. We want to. We don't want for people to like be afraid that if they vote and maybe there won't be enough voters, so people will be able to know this private data about them. So the way we tackle this in this contract is that we want to create something called anonymity set, right? Because if enough people vote, and if let's say again, if I have 1,000 voting power and I voted yes, but the end result will be like there will be 200 voters, and the tally in the end will be yes 1 million voting power and no 500K. So people will not really be able to tell what's my voting power, what was my choice, right? So this is called anonymity set. The more people and the more voting power participated in a specific vote, the more the greater the anonymity set. And when we have a sufficient anonymity set, we we protect our users, and it's harder for an outsider um, to tell anything about any specific voters. So we very simply introduced the concept of quorum to the votes, right? So if we have quorum and we say the quorum is 33, let's say we decide, I don't know, the quorum it will be 50% of all the state CFI, right? So if we have, let's say, I don't know, $10 million locked in CFI, I would say that $5 million is a pretty good anonymity set, because I don't know, I'm just throwing numbers, yeah, but I can assume that $5 million that no one entity or one person holds that much. So we introduce a couple of things. First, we introduce a finalize transaction. And let's assume for now that it is a public function, like everyone can call it. And we'll get back to what's all this in a second, but what we want to focus on for now is where is the quorum? Here is it. We check we basically query, we sum up the entire tally, we sum up the entire voting power participated in this vote, and we calculate the percentage of participation in this proposal, and we basically just check if it is greater than the quorum, that we say that this proposal is valid. And only if this proposal is valid, then I will reveal the outcome of this proposal. Okay, so if we get back to the example, so I can say only if $5 million worth of CFI voted on this proposal, I will reveal the outcome of this proposal. If this proposal didn't reach 50% of the stake CFI, the outcome of this vote will remain private forever. So no one never would be able to read or query or see the results of this proposal. Okay, so we've addressed this issue of the anonymity set. So this is cool. But I want to talk to you about another, like, let's say, attack vector. And I say attack in, like, I mean, like, let's say we have attackers that have that want to break our privacy or the user's privacy, and want to like take advantage of users' private data. So I want to talk to you about another attack vector, which is offline attacks. Okay, so let's erase all this. And let's say we have this proposal of, should we eat tonight? We can vote yes or no. And we have our blockchain, right? Let's say this is the state. And we have one transaction, two transactions, etc. And let's say on transaction 10, this is my vote. This is the vote of Tom. And I voted no with 10,000 voting power. Now, what an attacker can do with an offline attack? Technically, and this type of attacks is pretty complicated to implement. So this is not super trivial at all, but this is still something we want to address, especially if we have something really meaningful stored in a contract. So as I said, let's say on transaction 10, I voted no with 10K voting power. What an attacker technically can do is at this specific moment, if I'm an attacker, I can create a fork of the network, which is doable. And let's say the vote ended up like we had a ton of more transactions here, and we reached quorum, and we had like $20 million participated, and everything is good, and we have sufficient anonymity set, and everything's great. What an attacker can do is fork the network. If let's say an attacker wants to know what I voted for, he can fork the network at the moment of my vote, and let's say I am the first voter. So we can fork the network at the moment of my vote. And at this point, this is a fork of the network, so it's not really live. Like any action that's going to happen here is not really recorded on mainnet. I hope this is clear enough. If an attacker forks the network, an attacker can technically buy enough CFI to reach quorum in this fork of his, in this offline fork. So let's have the yes option and the no option. And let's say that to reach quorum, you need to reach to this threshold. Let's say this threshold in our case is, I don't know, 500 or let's say 50 million and 50 million. Let's say to reach quorum, we need a total of 100 million CFI, and to reach quorum with both options, we want to divide it 50 and 50. So an attacker can technically buy 100 million CFI, vote 50 million to option yes and 50 million to option no in this offline fork. What happens then? The result of this proposal in his offline fork of the network will be, what's the result is going to be? The tally is going to look like yes is going to be like 50 million point like 001, and no is going to be 50 million fixed, right? So this way, the attacker is going to basically reveal my vote. He reveals that I have 10K voting power, and that, in this case, I voted no, but you get the point. He can know that I have 10K voting power and the choice that I voted for. So again, as I said, this is not super trivial to implement, but this is technically possible. So the voter will, to summarize this up, the attacker will fork the network. He will vote for the two options just to reach quorum, and then he can basically know. He can single out a single vote, and he can know what this vote was for and how much voting power it used. So this is a very complex attack that can be solved with a very simple solution. We just want the finalized transaction to be permissioned. So if the attacker would not be able to call the finalized transaction, the results of this vote will never be revealed, right? Because we said to calculate, to like sum of the tally and figure out if this vote reached quorum or not, we need to call finalize, and this finalized transaction is basically um, is basically um, uh, I lost the word. It basically says that this vote is valid and reveals the results. So if the attacker can't, and this is something he can't change on an offline fork. If the attacker can't call this finalize function, he can't really reveal the results. So as I said, it's a pretty complex attack that can be solved with a pretty straightforward and simple solution. So in our specific case, just to not confuse you, we have a reveal committee. So we don't have a specific one person that can reveal results. We have a committee, a set of people. So it's acting like sort of a multi-sig function. So let's say we can say that we have let's say we have 5 people in the reveal committee, and we want 4 out of 5 people to like send a finalized transaction before the vote is actually finalized, and before we can say if the vote is valid or not, and to reveal the outcome of the vote. We have a question: is it possible to query the tally before the finalized action is executed? Thomas asked it. The answer is no. The whole point, and you're right to ask this, the whole point is you are not able to query. I'll show the query itself, where we have the query function. There you go, query tally. We have a function here that makes sure that the vote is both finalized, that is, it is ended, and that it is valid. If the vote hasn't ended yet or is not valid, we can't query the tally, or rather we can, but we won't get an answer, we'll get an error. Yeah, so that's about this attack. We have, like, I'll say a few words about another technically possible attack. Let's say we have this use case right here where we have a vote, and we have like an attacker created a fork of the network and is trying to figure out what was my vote, what Thomas voted. So as we said, for the vote to be valid and finalized, and for people to be able to finally query the outcome of the vote, we need to have a finalized transaction here at the end of the vote, right? We'll have a finalized transaction. Why wouldn't the attacker be able to replay this transaction on his local fork of the network and finalize the vote this way, right? He can replay my transaction, and replaying transaction should be like, again, it's not a trivial attack, but it should be doable. He can replay my transaction. He can, again, as we described earlier, he can vote for both the options just to reach quorum. And then at the end, he'll replay the finalized transaction, which mimics true finalization of the reveal committee or a specific person that can reveal votes. So this way, the attacker fools the mechanism, this mechanism, and he finalizes the results on his local chain, and then he's still able to query my vote for this proposal. So again, this is a pretty complex way of this is a pretty complex attack and is not trivial at all. But again, the result is pretty much pretty simple. And what we do, and we are going back as I promised to the vote function. And what we do is that for every vote that a user votes for a specific or for a certain proposal, we also create a hash or a rolling hash, we call it in this case. And this rolling hash, we initialize it on the init function. We initialize it with just zeros, right? We know where it starts. And for every vote that a user votes for a proposal, we update this rolling hash. So we we calculate here the new hash. This is a basic, like, I think it's SHA-256. So it's pretty straightforward. We just take we just take the current rolling hash, we take the message sender, and we take his vote. We take his choice and his voting power, and we also add salt from the user. So this is an additional entropy from the user to make it even harder for an attacker to take advantage of. And with every vote, this hash is updated. And what we do eventually with this hash is publicly queryable. We can query it here. We have a public query of rolling hash. We don't it's completely public. And the way we use this rolling hash is that on the finalize function, the reveal committee, or the people who reveal, or who has the permission to reveal the vote results, they need to query this rolling hash and then send it along with the finalization transaction. So you see that on the finalized transaction, I also expect to get this rolling hash. And then I read the rolling hash from my storage, and I make sure that I get the correct rolling hash. And what this gives to me, or to us as a contract developers, is that an attacker now can't fool the vote on an offline version of the chain, because what it creates is that an attacker has to have the whole chain of votes in order to reach the specific needed rolling hash. And because the rolling hash eventually is compared with the locally stored rolling hash that actually created inside the contract, which an attacker can't affect or doesn't have an effect on, the attacker actually can't fool or can't take replay specific transactions from the true live chain, or can't isolate specific transactions. And that way we preserve the anonymity set, and that way we still have the anonymity set, and the attacker will not be able to tell, again, let's say we have $20 million worth of CFI voted, he would not be able to tell which vote is mine, like what I voted for, or what my voting power was. Yeah, so we'll end it here. I think I hope I didn't confuse you too much with the offline attacks and all that. The main takeaway you should get from this session is that basically, first of all, we have a lot of cool necessary use cases that we can't implement in a decentralized way without built-in native privacy. And this is enabled by the secret network, which is very cool. And I hope you could see that getting basic privacy out of your contract or out of your code, getting basic privacy in the secret network is very simple. It's very trivial, and you get it for free. You simply can write the code, and the storage will be encrypted and private, and the inputs and outputs will be encrypted by default. All you need to do is just write the code, and if you have a very valuable or meaningful information, sometimes you also need to think about different kind of offline attacks or something a little more complex or more fancy. But basically, for like, I don't know, 95% of the use cases, I think uh, the privacy is enabled in a very simple way. And as I said, you basically get it for free. So thank you very much for listening. And I'll if we have I think we have like 15 or maybe a little less minutes for questions. And I will also say that I have a bunch of links here. So I will send you the slides in the chat, and you'll be able to see these links. The code itself on GitHub is linked here, the secret voting contract. And if you are interested in exploring the secret network space in general, or like understand how you start developing, or like how do you get started on secret network, you have the other links as well, and you are more than welcome to ping us on the social links on Discord or Telegram. And yeah, does anyone has any questions? Okay, so yeah, so I think we can wrap it up. As I said, if you have any questions or want to talk about anything, you feel free to ping us on Discord, on Telegram. This is my handle, TomL0101. Yep. Thank you very much for having me.